a question. Oh, good, I'm on. So anyway, let me see if I can get this looking a little bit better here. So Anna hates me.
That's exactly what she said. No.
Hey, not everybody. Hey, I get it. Not everybody likes chemistry. That's fine. You know, I don't like.
You are a great teacher.
I don't like Shakespearean literature. You know, and so what I remember what I was talking about. I said that we our atoms. Let's say I've got some sort of homonuclear diatomic molecule, like for example N2. N2. Homonuclear means I have a diatomic molecule and both my atoms are the same. Okay? That means they have the same electronegativity, but they come together and they form a molecule. And we have to take the atomic orbitals and then mix them up. Remember I said, we have these atomic orbitals and these wave functions, and we can make combinations, and we can come up with molecular orbitals. And I call them LCAO-MO, linear combinations of atomic orbitals give molecular orbitals. And that's all that means. So we are taking, let's say I have the nitrogen atom, and I've got a nitrogen here and a nitrogen here. Oops, that's not a very good looking nitrogen. And this is the 1s orbitals, the 2s, and the 2p. And I said, hey, when these orbitals get together, I have two atomic orbitals, they get together, and they're going to do something. They're going to make two molecular orbitals, one at a lower energy, that's called a bonding orbital, and one at a higher energy called an anti-bonding orbital. Anti-bonding orbitals mean that those electrons that occupy those orbitals are going to try to not bond. So, and we gave these names. We said, well, the s orbitals can come together to form the sigma 1s and the sigma star 1s. The sigma star was the anti-bonding, and the sigma was the bonding. Likewise, up here, we have the sigma 2s and the sigma star 2s. Okay, and then here we've got 1, 2, 3, 4, 5, 6 atomic orbitals, and n atomic orbitals give n molecular orbitals. So I have to make 6 molecular orbitals. And in a homonuclear diatomic like this, you're going to have a sigma 2p, and these are going to be pi 2p, pi 2p, pi star. These are higher energies. 2p, pi star 2p, and sigma star 2p. Okay. So let me show you how we could take a molecule like nitrogen, reconcile it with our Lewis structure, and how all these ideas harmonize together beautifully. So each nitrogen has 7 electrons total, and we have to use them all, not just the valence electrons here. So what we're going to do is we're going to take those 7 electrons, so I have a grand total of 14 electrons, and I'm going to fill my orbitals, just like in the old days when we were doing 1s2, 2s2. So I'll use a different color. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Remember Hund's rule, you want 1 in each before 2 in any, right? Okay, all the rules work. So this is how we would write the molecular orbital representation of this molecule. Yes, Anna?
Why didn't you write one on the top like you did on the rest of them?
Say that again?
Like on the top of the shape, right up there. No, why?
I ran out of electrons.
Oh, okay.
Yeah, you have 14 electrons. You can't add any more. But you just gave me a great idea for a test question. So, anyway, what? That's because she hates me. Sorry. I'm joking. I love you guys. So anyway, this BO does not stand for body odor. It stands for bond order. Bond order. Now, the bond order, is it single double, triple. Well, the formula is bond order is equal to 1/2 times the number of bonding electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals. So let's count this up. We've got, and if we want to write it out, we could say sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. I'll come down here, sigma 2p2, and then pi 2p. I have a grand total of 4 in there. So let's add up all the bonding electrons. I've got 2, 4, 6, 10. So I've got 10. And now let's add up all of the antibonding electrons. 2, 4. That's 1/2 of 6. 3. Bond order of 3. Lewis structure gives a 3. And this is another representation of yeah. It's when you really start studying this stuff, everything harmonizes so beautifully. And I'm only giving you little snippets here and there. So what I could say something like this. What happens? What would the bond? Yes, Anna.
The star ones are anti-bonding.
Star ones are anti-bonding. I could say something like this. Does this species exist? Let me think of one here. What is that sound? Oh, does that species exist? If it does, what's the bond? Is it theoretically possible to have this some sort of a diatomic fluorine with a +2 charge on it? Well, you'd have to think. I've got 18 electrons, but with a +2 now I have 16 electrons. So you'd have to fill it up and then do the bond order calculation and see, is it possible? Is it likely? What would the bond order be? Yeah, just things like that. But that's all I want to say about the molecular orbital theory. I want to talk about a very exciting thing now that you don't normally ever get in high school. I don't know any high school, unless maybe it's a science high school, that talks about the following topic. And again, this is not on the test, but it's fun, I think. So I'm going to talk about something called polarity and molecular symmetry. Polarity and molecular symmetry. You should be able to know whether a molecule is polar or not. And I'm going to show you a basic way to do it, but I'm also going to show you a fun way to do it, I think. So polarity, basically in a molecule, means there's charge separation. So I have a molecule like water, and water is very, very polar. It dissolves ionic salts, which are very extraordinarily polar. You have positive ions and negative ions, and the water just rips them apart. Well, what we say is there's charge separation. So this part up here is going to have a partial negative charge because oxygen's very electronegative. It wants to suck those electrons toward itself. And this part down here is going to be, that little squiggly thing means, it's a lowercase delta, means partial positive charge. So what we say is this molecule is polar because there's charge separation in the molecule. Just like a magnet has a north pole and a south pole, right? And I look at it and I'm saying, okay, we can also represent it like this. That shows the direction of what's called the dipole moment. And that's just a fancy, that's just a fancy word for saying the positive part's down here, the negative part's up there. So I'm going to pause this video. You don't need to see it. So anyone who's not here, don't worry about it. So I hope this helped, whatever we did here.